Let's just briefly see the flow of ideas, intermediate steps that we had towards the final statement for sequential compactness. Okay, so this is what we had last time. We just say that a metric space is sequentially compact if every sequence has a convergent subsequence. And the point is that, okay, so one version of the Heine-Borel theorem says, characterizes sequentially compact sets inside Rn. And these are precisely the sets that are closed and bounded. So the word closed and bounded, they both depend on the metric that I put in Rn, a priori. But the metrics that we are interested in, we are normally interested in the Euclidean metric. But we saw that the topology that we get by the Euclidean metric is the same as the one that we get from the p equals 1 norm and the p equals infinity norm. And similarly, the notion of bounded also stays the same in all three scenarios, p equals 1, 2, which is the Euclidean case, and infinity. Okay. All right. So the Heine-Borel theorem says that the subset is sequentially compact if and only if a set under consideration is sequentially compact if and only if the set K is closed and bounded. Now, two things to say. One, which is our main goal today, is to prove the exact same statement by dropping the word sequential. So a subset in Rn is compact if and only if it is closed and bounded. That is number one. The second thing is that the definition of compact, when you encounter it for the first time, is not necessarily very intuitive. Nonetheless, experience shows that it is a very versatile notion. Okay. Hopefully, the notion of sequentially compact is a bit more palatable. You saw it, after all, for real numbers last semester. Now, it is a general fact that for a metric space, sequentially compact and compact are synonymous. So if we take that for granted, then the claim that I have written over here follows if I drop the word sequential. Now, we are not going to take that approach. Okay, we are going to prove Heine-Borel for characterizing compact sets of Rn completely today. Maybe a little bit in the next class. But okay, so this is what the overall is. All right. So, and recall what our scheme was last time. So I've written it in the steps. In one direction, we first showed that the closed interval is sequentially compact. Then by taking product of such closed intervals, we saw that a box is sequentially compact in Rn. Then from that, we said that any closed and bounded subset of Rn is compact. I assigned this as a small exercise to you, which we will discuss in the middle of the class. And then in step 4, we showed the converse, which is that if I have a sequentially compact set, in fact, in any metric space, then it must be closed and bounded. So in particular, the same is true for Rn. So we are going to follow the exact same strategy for compactness that we showed for sequentially compact. So that's what we are going to do today. All right, so this is the skeleton, and let's begin. So before we start, are there any questions? Very well. So let me now write down the things that I just said. So take a metric space and K is a subset of X. So remember, K itself becomes a metric space. Sorry, I should start recording.
Recording in progress.
Okay, so we are going to work inside a metric space X, and any subset also becomes a metric space under the same metric. So let us define what compactness means. So suppose I have a family of open sets indexed by some index set I. Okay, so an open cover of X is just a bunch of open sets whose union is X. We say that X is compact. So this is not really definitions, this is definitions. So this is one. Which is to say, suppose I am given whatever family of open sets whose union is X, then no matter what the family is, I should always be able to extract a finite number of V alphas whose union is X. If such a thing happens, then I call X to be compact. This is an extremely useful notion, as we will see, as you will see, not in just this course, but multiple courses. Okay, so remarks, several remarks. So one, maybe if okay, so just look at this definition. You see that this definition is only in terms of open sets and unions. Such a thing makes sense not just in any metric space, but also in any topological space. So you can apply this to any topological space. Likewise, the definition of sequential compactness also makes sense in any topological space, as soon as you define what convergence of a sequence means. So remarks one, any X then We will not prove this. If you want, you can take this as an exercise. Uh, this is not true in general. Both implications fail. And if you want, you can take this as an exercise. All of this. The second remark is much more important for us at the moment, which is that let's see what it means for a subset of this metric space X to be compact. Now, you can say, well, no definition is really required because I already have the definition of compactness for any metric space, and a subset of a metric space is a metric space. But let's see what it means for so reformulation. Compactness for subset K of X Okay. So what does it mean for K to be compact? It means that every open cover of K has a finite subcover. So let's write this down. Every cover of K Okay, but what are open sets of K? Remember, open set of any metric space is a union of balls in that metric space. But balls of K are really just balls of X intersected with K. So to take a union of balls in K is really the same thing as saying take the union of the corresponding balls in X and intersect that with K. In other words, open sets of K are really just some open sets of X. Let me start that sentence again. Any open set of K is of the form open set of X intersected with K, and vice versa. Which is to say, if I take an open set of X and intersect it with K, then I will get an open set of K. Okay, so this is to say we have the form. If and only if. So let's run through this. If K is compact, that means that if I'm given any family of open sets of K covering K. Now, what does that mean? Now, every open set of K in that family is going to look like some open set of X intersected with K. So this family is going to be of the form V alpha intersected with K. Any family V alphas are open in X. V open X. What should happen? If this family, every family like this with V alphas open in X, if it covers K, then there must be a finite subcover. Now, here's the point. By the way, this is very small, but now what does it mean that V alpha intersection K, its union is K? How can I express that in terms of V alphas themselves? For a family V alpha, of open sets in X, such that, what is the condition now? So V alpha intersected with K, their union is K. That means that what is the corresponding condition for V alphas?
The union of V alpha must be a superset of K.
The union of V alphas, alpha in I, must actually contain K. Notice that the two things are exactly synonymous with each other. Because if V alphas altogether miss some part of K, then after intersecting with K, I will still miss that part. There must be a finite subfamily V alpha 1, V alpha n, with union of V alpha i's containing K. So this is sometimes given as a definition of a compact set. But you see, it's really the same definition. There is really no difference. So what we will do is that we will use the word open cover to denote even this slightly more general situation. So we will say that that a family of open sets in a topological in some topological space X covers a subset if its union contains that set. And from this, I can get a cover in the original sense just by intersecting these open sets with the subset itself. So this is a very simple set theoretic point, and I hope that there is no confusion about this. I mean, the point that one is trying to make is the following. You see, suppose I have a space X, a subset K, and suppose I take some other subset U, all right? And let's say this subset U is inside K. Now the question is, if I ask the question, is U open? Then that's an ambiguous question. Because there are two topological spaces under consideration over here. The ambient space X as well as the subspace K. So my question really does need to be modified to make it more precise. However, if I ask a question, is K compact? Then whether I regard it as a topological or a metric space within itself and apply the first version of compactness, the first definition of compactness, or if I regard it as a subset of X and use this box definition of compactness, if I take this as the definition of compactness, I will get the same result. So let me write this as a remark. If I take of a subset as the definition of compactness of a subset K of metric space X, then K is compact as a subset of X if and only if K is compact this is what that little reasoning over here, the reasoning that I wrote over here, that's what so this reasoning over here basically is justifying this fact that I wrote at the end. Okay, so any questions so far? This was really just setting the scene, nothing more. What you should think of, this little bit that we did is that unlike the words open or closed, when multiple topological spaces are involved, when you have a space as well as a subspace, unlike the notion of closed or open, the notion of compactness is intrinsic. Okay, so all right, so let's draw a line under this and start doing more interesting things. Actually, let's start working with so goal. So closed and bounded sets, subsets of Rn are precisely the compact sets. And again, remark with respect to so if the norms are equivalent, then the notion of closed or open stays the same because they induce the same topology. And whether a set is bounded or not is also the same with respect to any one of them. Okay, so later on, of course, we can replace this with any P. because we will show, in fact, using Heine-Borel theorem, we will show that all norms on Rn are equivalent to each other. Okay, so any questions so far? Very good. So remember, there are no wrong questions, right? So if you have questions, please do stop me. Especially since I do not get to see your faces, I do not always know whether I'm going too slow or too fast or if it's making sense or not. Anyway, so the steps are going to be exactly the same as before. And I will number them the same, that closed interval in R is compact. So let us just say 0, 1 today. Or okay, why not? A, B is compact in R. Then closed box, which is, I just take the product of these, which is A1 comma B1 cross to AN comma BN is compact in Rn. So of course, what we will do is we will use number 1 in order to go to number 2. By the way, I should have said this. Let's go back. So we said that this can be with respect to any norm. Which one will we use? Which is the most convenient one?
Infinity.
Right. And we've sort of seen this now at least 2 separate times, right? In the lecture before the previous one, towards the end, remember what we saw, that using the infinity norm, it was easiest to see that convergence of a sequence in Rn is really the same thing as slot-wise convergence, that it can be tested using slot-wise convergence. Then last time, when we were doing parallel development for sequential compactness, again, we saw that being able to consider things slot-wise is good. And so we use the P equals infinity norm. So here also, we will see some way of doing this in a slot-wise fashion. And if you're bored, you can try to prove number 1 and number 2. So these are the, this is where real action lies. Steps 3 and 4 are also nice, but that is softer stuff, really. Okay, so how does number 1 and number 2 allow us to prove the backward direction? Because the backward direction is the one that is saying that certain kinds of sets are compact. Now we have shown that, assuming steps 1 and 2, we have shown, those steps would show that a closed box is compact. So how do I go from that to an arbitrary closed and bounded set? Well, I prove the following. This is the easiest of the lot. So you can think of it if you want. And number 4, okay, so before we go to number 4, let's that.
It should be a closed and bounded subset of convection.
Okay. But you see, not necessary. All right. So we will see this. But you see, if the bigger set is already given to be compact, then by Heine-Borel, it is already bounded, right? So a subset of it will also be bounded. I mean, this is an after the fact logic, but it shows you that boundedness of the closed subset is not really required. It's automatic.
Okay.
So Maybe not this. So these steps would give the backward direction of how? Can you see how? So let us say assuming steps 1, 2, and 3, or rather just 2 and 3, because 2 builds on top of 1. So that's, can you show me now that clay K must be compact? This is not difficult.
We can put a box around K.
Correct. So if K is bounded, then we might as well use P equal to infinity. That means that in each one of the slots, it is bounded. So everything in the first slot is within some interval. So pick some large bound that works in each slot. So as a result of this, what this says is that K is, let's say, in some large box. Let us say minus M to M, some large bound taken n times. And this is, what do I know about this? This one is compact by step 2. So what this is showing is that K now becomes a subset of a compact set, but K was given to be closed. A closed set in Rn is going to be a closed set of any subset that it, of anything that. So that's not coming out right. See, if I have a space X and a subspace S, and if some set K is a subset of S, so K is a subset of S, which is a subset of X. Now, if K is closed in X, then it is automatically closed in S. Is this clear? Because remember what we said? Closed sets of a subspace are closed sets of the big space intersected with S. So if this closed set was already part of the subspace, then intersection doesn't do anything and it remains closed. So thus, is a closed all right. So, and then number 4, which is the converse direction. So proof of so what is the converse direction? It says that any compact set must automatically be closed and bounded. And in fact, this is true not just for Rn, but this is true for any metric space. So let's see this. Okay, so okay, so this is misbehaving a little. All right. In any metric space X, right? Let me see if I can go back and open this again to see if then K is closed and okay. So this is how we are. So this is how we have laid out everything. Now let's look at these. Let's do these things one by one, and we will begin with number 4. So proofs. So 3 is the easiest, and 1 and 2 are sort of the meat of the matter. So let's get number 4 out of the way. So K is compact, implies K is bounded. So this is a one sentence proof. And let us look at the definition of compactness to see what needs to be done. Okay. So I'm given a compact subset of X. What does that mean? It means that if I give you any family of open sets, V alphas, whose union contains K, then K must be contained in a finite union. So that's what is given to me. And somehow I want to deduce that K is bounded. Okay. What does it mean to show that K is bounded? So let's write
some ball which K is contained in.
Correct, exactly. So let's do this. K is contained in some B, some ball X and some large radius, right? Let us say, okay, so let's say, right, for K is compact in XD metric space, for some X in X and R greater than 0. So where am I going to get this ball? I want to use compactness. That means that I probably should take some open cover. Which open cover can I take? And
So
rather,
hello?
yeah, go ahead, please.
Yeah, we can take the same center but with increasing radius. So that's a open
Yeah, so
cover.
this is a very simple idea, but you should see it once. Consider. Oh, sorry, B. And in positive integers. So basically, I am simply taking ball of radius 1, 2, 3, and so on. Right? So this is a cover of K, but in fact, it is a cover of X also. Of X and hence of K. But in fact, so when I say hence of K, I am using the slightly more general notion of the cover. That is, these are open sets of X. But I can still say that they cover K by taking intersection with K if you want, using the earlier definition. So this must have a finite subcover, and that finite subcover will be B N1 X And then what? Then I'm done, right? Because you see these balls really, they're expanding. So I simply take, so what is take R to be? What? Come on. So I want to show that K is bounded. That means I need to show that K is contained in the single ball of radius R. So what is the radius that I take?
Maximum of n1 and 2 nk. So nk. Oh, actually.
Okay. And by the way, so x is really any point. So this is easy. So that was one thing. But now I need to do another one, which is that claim is that K is compact, implies that K is closed. And this is a nice little argument. And it is a prototype of arguments that one sees routinely. Okay. So if you're seeing this for the first time, pay attention closely. Because it's not a, it's a useful type of argument that one does again and again. I'll give you some exercises that do this type of argument. Okay, so how does this go? I need to show that some set is closed. So what does it mean to proof? X minus K is open. That's what it means to show that a set is closed, correct? Now, how do I show that a set is open? So remember this picture of open sets. Open set means that around any point in that set, I should be able to put a small ball centered at that point, which is totally contained in the set that I'm trying to show to be open. So this is what we are going to try to do. So let's do this point by point. So let us pick some point. Let's call this point, pick some X in this set, which just means that it is not in K. So let's draw a little picture over here, right? So this is, let us say this is K. And I have some point X here. What I want to do is, and this set here is K. And what I want to do is I want to put a small circle around X that does not intersect K at all, right? If I'm able to do that, then I will be done. So let us say enough to. Enough to construct an open set. And in fact, let us use our terminology, an open neighborhood UX of X with what property?
Does not intersect K.
That does not intersect K, right? So such that UX intersection K is. So is this clear? We are simply putting the various players in place. We have just putting in place a strategy along with a requisite terminology, right? So, okay. All right. So where is this set going to come from? See, the point is this set X could be quite close to K. So I may need to take the set UX to be small. And I need to have some kind of mechanism in order to do this. All right. So where does the compactness of K come in? And this is how it happens, right? So how to get this?
Sir, like, can we decrease R can we like keep
Yeah.
counting back from R to 1 and then go to 1 by n?
Right. But you see, okay, so but I have to at some point become quantitative, right? As in, how small should R be?
R should
And
be
that
a
is,
maximum of n1 nk from the previous.
so see, somehow I have to use K, correct? So you want to
Yes.
take, yeah. So
So
you want
there
to
should
take
be
a
a finite
radius 1
subset.
by n. So how small should I take it?
I mean, there should we should first set a collection of balls that starts from R, goes to 1, and then 1 by 2, 1 by 3, etc. So there should be a finite subcover
But subcover of what?
of K.
Yeah. So you see, I have to first have a cover of K.
This will cover K because R, we proved that it is uh, bounded. So R will it will be a subset of R. So it will be a cover.
Yeah, but you see, I want to cover K, right? That means every single point of K should be covered. And you're right, we will do that, but let's do that systematically. So how do I find a cover of K? And where is the finiteness going to come in? You see, it works out very nicely. So here. So for now, or not, let's not say fix. It is, I have picked X. Let us, so this X is fixed, okay? So now take some Z in K. So here is my Z. And let me lay out the strategy. It's very simple. So what I want to do, see, if I want X to avoid every point in K, then in particular, I have to avoid Z. So how do I ensure that this neighborhood of X avoids Z? That's very easy to do.
So we can take the distance between them and half it.
Correct. So I can take the distance between them and take half the distance. Now that will avoid Z, right? Okay. But this is what I want. This is what I will do. You see, I want to go a little further in this direction because I want to use compactness of K. So you see, okay, so let's take this strategy. That means that I take the distance between X and Z, let's call it R, and I take a ball around X of radius R by 2. That's how I have avoided Z, right? But I want to avoid every single Z. What does that mean? That means that I have to take this distance R and take half of each one of these distances between the fixed X and the varying Z. And somehow I want to say, oh, there should be a minimum distance, correct? That all of these R's, there must be a positive minimum that I can take. But that positivity is not clear, no? For the Z that I have drawn, I may need some distance. But as I take Z closer and closer to X inside K, maybe the required radius will keep going down without any limit. Maybe the limit of all of these required R's is 0. And in which case I'm in trouble, no? Because I want to find finally a single ball around X that avoids everything, that avoids all of K. Okay. So I hope that the difficulty is clear to you. So we have to be cleverer. So what we should try to do, or what we can do, this strategy will work, is that we will not avoid just Z, but we will avoid a neighborhood around Z. Okay. So this is what we will do. So let C be, or whatever, something, or R maybe. Okay, C doesn't really matter. So let this be the distance between X and Z. Now I will put balls not just around X that avoid Z, but I will put balls around both Z as well as X that totally avoid each other. So this is the picture that I want. And let me change this. So let's do this. So I want this, and I have a ball around X. So I want these balls to completely avoid each other. And just to make things sort of not give false impressions, this set K may very well be like that. All I care is that the circle around X and the circle around Z avoid each other. We will see why this is useful in very shortly. But can I do that? So what you said is that around X, I can take a circle of radius, a ball of radius C by 2. Okay. But what about around Z? So here what I want is the following. Then the ball of radius around X and ball of some radius around Z, their intersection is 20. So what radii should I put over there?
C by 3 for ball.
Yeah, so C by 3 will work. Will C by 2 work?
No, sir, at a single point.
But you see, this will still be all right. The
But
reason
sir, they
is
are open, right?
they are open balls. Okay.
Yes, sir.
So if I take C by 2 and C by 2, it will still work. But let's, this is really nothing delicate is required. So let us take C by 3, C by 3. And what is the reason? Why do these two balls not have anything in common? What is the magic phrase? By
So the triangle inequality.
the triangle inequality. All right? By triangle inequality. So do we need to write this down? Okay, so might as well. If some point y belongs to this intersection, then what will happen? Distance between X and Z will be less than or equal to the distance between X and Y plus distance between Y and Z, which is less than or equal to C by 3 plus C by 3, which is 2C by 3, which is a contradiction because this distance is C, which is a contradiction. Okay. So things of this nature, we should just be able to do from now on without sweat. Right. So this is the reason. Okay. So what I'm going to do is let's call this set, let's give these sets some names. Let's call this set to be let's call this set to be V sub Z. And let's call this set also to be not indexed by X, but let's call this to be indexed by Z again. So W sub Z. Because remember, X was fixed even before choosing W, right? So this is the set. All right. So now what's going to happen? We have our beautiful open cover. Note that union of which sets? VZ in fact, let's not take the. Of course, this union is. This union is contains K because I'm taking a point around every point in K, right? So VZ is an open cover of K. By compactness, we have VZ1 union up to V some Z N contains K. Now comes the clever part. So you see what I am doing is around every point of K, I have put these balls. Now only a finite number of these balls are covering K. What do I want? Remember our goal. Our goal is to find this UX such that this happens. This is what our goal is. So where is this U going to come from? I want to avoid K. All right. So how do I get to avoid K? Now only one small trick is required. And then our job is done. As WZ and VZ do not intersect for all Z, what happens if I take the corresponding W's, W1 up to W of Z1 up to W of Zn? So what's going to happen is that, so let's draw another picture over here. Here is V1 or VZ1, VZ2, VZ3, and so on. Okay,
So the
this
finite intersection of
so
these
this-
balls.
So you see, this picture is a little hard to draw, but maybe I will still try to do it. Let's see if I can do this. So here is for Z1. Let's use now different colors. Now here is the circle for no, let's not do that. Now here is red circle, right? But it is disjoint from one. And let's use another one. And let us suppose that there is this blue circle, which will intersect with but there is another one. Okay. So what are these? This is VZ3, or let me not use the Z's here. So let us say this is V3, and now I have W3. And likewise, I have the first one, which was V1. And the black one here is W1. And the red one, let us say V2. And here is W2. So you see, there are all kinds of, the picture may look bizarre. The point is that all the V's, I want to take their union in order to enclose K. So if I want to avoid K, then I want to be inside the black W as well as inside the red W as well as inside the blue W, right? If I do that, then being inside each one of the respective W will avoid the corresponding V. So if I'm inside all of the W's, then I will avoid each one of the V's. Intersected with K is equal to empty. what was the purpose? So where did finiteness help us over here?
Finite intersection of open set is an open set.
Exactly. So you see these W's, I could have played the exact same game by taking intersection over all the W's. Would that intersection be non-empty, by the way?
Yeah, because X is in each one of them.
Exactly. So you see, the non-emptiness is not the issue because X is in each one of them. However, that infinite intersection, for all I know, consists of only X. It need not be open. However, this is a finite intersection of open set. So now I am done, home free. Finite intersection of open neighborhoods of X. So call this U sub X and we are done. Okay. Any question about this proof?
Sir, not a question, but what I said before was wrong. I just wanted to say it.
Right, but you see, maybe, I mean, it's not clear to me whether it was wrong because I didn't quite understand what your idea was. So,
Sir, it was completely wrong, sir. Just wanted to say that.
So anyway, what property of this V's and W's made this work? Okay, so that's a bit bad, but let me just so key fact. Let's try this once. So key fact. For X not equal to Z in X, we open neighborhoods of X. Open neighborhoods V and W of X and Z respectively such that V intersection W was. That's all that's where we use the metric space and triangle inequality. But after using that, the rest of the argument was relied only on topology. Okay, so topological spaces that so check what we proved. In a Hausdorff topological space, any compact subset K is okay. What were we proving?
Closed.
Is closed. K is. So this is just an aside. So this is a remark. And I'll put this is, if you care about this kind of stuff, you can see it. Otherwise, you can safely ignore this. because you will do this anyway. All right, so this finishes step 4. So let's now go to step 3, the easiest step. So what we want to say is claim C a closed closed subset of a compact set, and I might as well call it X, because everything is happening in compact X implies C is compact. And this is very easy. So take open cover V alpha and let's use our second. Take cover of C by open sets in X. That's what we will do. Right? Remember that it doesn't really matter, because open sets of C are intersections of open sets of X with C. So what we want to show is that this closed set is compact, which means I have to take an open cover and show that it has a finite subcover. So union of V alphas contains C. So I'm going to use compactness of X, which is the reason why I took open sets in X rather than taking open sets of C. So what do? I want to use compactness of X. That means I should have some cover of X. So what do? Note that
Take C complement.
V alpha in I union X minus C. So as simple as that. So I have some collection of open sets whose union contains C. I just throw in an extra open set, namely the complement of C. It is open because C is given to be closed. And all the V's together cover C. So if I throw in the complement of C, that will cover all of X. So there must be a finite subcover. And this finite subcover, that will work. Because this finite subcover, it covers X, no? So of course it will cover C. The only small thing is that I want a subcover of the given cover. So there it may be that the set X minus C was used in order to cover X in this finite subcover, but I can safely drop it. No? I don't need any of that to cover C. By compactness of X, the same subcover works for C. Okay. All right. So any questions so far? Remember step C in the last class I left for you, which was this exact same thing where the word compact is replaced by sequentially compact. So if I have a sequentially compact space, And if I take a closed subset, then it is automatically sequentially compact. I hope you did this. The proof of this is very easy. It relies just on the fact that if you have a closed set, then any limit points of that are contained. Okay, so now for the most interesting part, and we are almost out of time. So I can just get started. So what remains is steps 1 and 2. So 1. Let's say open interval AB is compact. So proof. Suppose some V alpha is an open cover. I need to get a finite subcover. So let us just discuss the strategy and then we will have to stop. Okay. So here is the thing. So here is A and here is B. So what does it mean that this V alpha is an open cover? By open sets, let us say in R. You see, what it means is that every one of the points every one of those points in the interval is covered by one of the V alpha. So let's say if I take a point here, then some of V alpha contains it. And remember, V alpha is an open set. So it is a union of open intervals. Now, a general union of open intervals can be quite complicated. Okay? Because those open intervals could be spread all over the real line in some way. Nonetheless, because this point is contained in some V alpha, that means that there must be some interval like this, which is contained in V alpha, which the V alpha that contains this point. So I could simply ignore the V alphas and I could simply say that for each one of these points, for each one of the points of the closed interval, I have some open interval around that is part of some V alpha. Okay, so how am I going to get this finite subcover? Well, I could try the following strategy. I simply travel from one end to the other. So I start with A. That means that A must be contained in some set of this kind, right? The reason why I put this open parenthesis on the left is because I am taking a cover by open sets in R. Okay, so very good. I have covered A. Not only have I covered A, I have covered some small segment of this closed interval from A up to some point. Let us say A plus, let's call this something. Let's say A plus some delta. Okay, so let us say that A to A plus delta. Oops, that's wrong. Because remember, so let's say, say that this is not contained. Is contained in some V1. So I take that V1 because I want to. Now what do I do? Let us say I take A plus delta and I put some open interval around that. Okay. So let us say A plus delta will be contained in some open interval. So this is part of something which is contained in some open interval. So you see now my picture is now small. In some, so here is my A plus delta and it is contained in something which is So this is A plus delta. And this part over here, which is contained in V2. Okay, so now what have I done? This A plus delta. So that means in the first one, so the picture is now small. So I had this, then I have something like this. All right, so I have gone a little further. So maybe I call this delta 1, and then I call this A plus, this one is A plus delta 2. So I have now covered everything from A using V1 and V2. I have covered everything from A to A plus delta 2. And now here comes sort of the hard part. What I'm going to say is continue. What is wrong with this?
We could have smaller and smaller and smaller intervals.
Right.
And
So you see the length of the first one could be, let's say, 1/3. Then the length of the next one could be 1/9. Then the length of the next one would be 1/27, and so on. So you see this geometric progression, it is going to sum to something less than 1. So I just may not get there in finite number of steps. So somehow I have to be cleverer than this. So you can think about how one could try to overcome this. But we have to stop for today. So we will take it up from here. It would be good if you can try to think of this proof on your own. And especially then go on and see how to go from one closed interval to a product of closed intervals. There is another sort of very nice kind of reasoning over there about handling slices one at a time. So if you read this, then we can go a bit faster next time. But today, let's stop.
Recording stopped.
All right, so I think the attendance is going down. I'm not really sure how to interpret this. One possibility is that people are just finding things easy, so they are not attending and will be doing work on their own. And I'm perfectly happy with that. But if people are already lost, then I need to hear about that. One idea is that, see, my office hours are not really getting used. So one idea is that I could simply require each one of you to meet me, even if it's for 2 minutes during office hours. And perhaps we can have a rotating cycle that every day, maybe in an hour, maybe during every office hours, maybe a quarter of the class meets me. That will be around 15 people. So I can spend like 5 minutes with each person. And we could rotate like this in a 2-week cycle. Let me think about this, because I want to ensure that nobody is really falling behind. We have already made substantial headway into topology. Still, it is early days in the semester, and if there are any problems, there is time to remedy this before, to address the problems before it becomes late. All right, so let me put it this way. If you are having any trouble, or if you know somebody who is having trouble, then please seek me out in the office hours tomorrow. All right. And it does not really matter if you come with saying that I don't understand anything. Okay. So that at this point, it is an acceptable answer, but very soon it will stop being acceptable. Right? So if there is a problem, we have to nip it in the bud. So if you have a problem, please seek me out tomorrow, and then we can try to form a study plan that is useful to you. I can suggest some simple exercises just to get you up to speed. All right. So for tomorrow, I'm going to keep it voluntary. If I do not have any response by tomorrow, then from next week, I will have a mandatory thing where people just have to meet me. Even if it's for 1 minute saying, I don't have any problem, everything is good. All right. So recall, office hours are in the same window as the usual class time. So tomorrow, 11:50, I will be there. And If you'd like to talk to me, and if you would like to talk to me individually, just send me a message beforehand, and I will just talk to you one by one. Okay. So, is there anything else to discuss?
Sir, in a arbitrary metric space, a Cauchy sequence need not be a convergent sequence, right?
So let me. Yeah. So first we have to define a Cauchy sequence, and is that okay? Can we define a Cauchy sequence in any metric space?
For a sequence, their existence is that for nm greater than capital N, an minus d of an minus am is less than epsilon for all epsilon. Their existence.
So of course, the for all epsilon should have come at the beginning of the phrase. Right?
Yes, sir.
Because whatever you do later on is dependent on the epsilon. Yes. So we can perfectly well define a Cauchy sequence in a metric space, and certainly a Cauchy sequence need not converge. Can you give me an example of such a metric space?
So I'm not sure, but maybe Cauchy sequences don't converge.
I mean, there are tons and tons of those, but okay.
The rationals.
Right. Okay. So, and in fact, that's sort of the whole point, right? You can complete a metric space. But there are other examples. You can just take, for example, open interval 0, 1. How about open interval 0, 1?
We can make Cauchy sequences go into 1 which don't converge.
Right. Or, just take 1 by n or something like that. With the standard metric, right? I mean, you see, your space itself is open interval 0, 1. So your Cauchy sequence, so 1 by n is a perfectly good Cauchy sequence. It wants to converge to 0, but 0 is not there. So that means in this space, there is a Cauchy sequence that does not converge. And that's kind of the point. Oh, so this is a one construction of the real line, is that you take rational numbers as a metric space. Now, this is a bit bizarre, okay? Because if you say metric space, logically, this is not really permissible. Because if you say metric space, you are saying real numbers. So I really cannot use metric space terminology in order to construct real numbers. Right? I mean, it's circular. In the definition of a metric space, I say that the distance is a non-negative real number. But nonetheless, without using the word real number, I can still do this. Anyway, sorry, I'm just talking all over the place. So the answer is yes, absolutely. We have lots and lots of metric spaces that are not complete, and we can complete them in a manner analogous to how one constructs real numbers from rationals. All right, so anything else? How about the metric space that you told me about last time? Discrete metric space. That is, the distance between any two distinct points is 1, and distance between any point and itself is 0. Is that complete?
I think so, sir. For a sequence to be Cauchy, it still does have to be eventually constant.
Right. So that's a complete metric space. Okay, so maybe one sort of One remark, see, we should not forget of what our brief in this course is. Our brief in this course is to do calculus, right? So the important notion is of a non-linear space. If we talk about metric spaces, then it is a much more general structure. What is addition of 2 points in a metric space? What is scalar multiplication? What is this homogeneity requirement? So metric space is a much larger class, and topological spaces are even larger. Okay. Now I've introduced this terminology, especially metric spaces, just because it is useful to talk about distances. Right? A general topological space, I simply introduced it just because it was easy to do so without much work. But our focus is really going to be on non-linear spaces because we want to do calculus over there. So a general metric space, what happens in that? And even a general topological space, those kinds of considerations, we can talk about it, and we are discussing a little bit here and there, but it is not germane to what we want to do. Finally in our metric spaces, things are going to be vectors, and those vectors are going to have sizes. And so we are going to define, so we have norms. We will define norms on operators, which is what is something that will allow us to define a derivative. A derivative is going to be a linear map. And as this linear operators are going to have norms. That's where we are headed. So I mean, you have entire courses, no, later on. You'll have a general topology course, and in your analysis 3, you will talk more about metric spaces and how to do analysis, maybe in more general metric spaces. And literally, there is like so many different directions in which one can go. You can do functional analysis, harmonic analysis, measure theory. We're just seeing some basic words that you can take in many different directions. And soon, it's taking a little longer than I would have liked. But soon we are going to complete this topology of RM business. Once we do Heine-Borel, then really there isn't a whole lot more. I mean, we will see what some properties of compactness, but then we are going to get into actually defining the derivative. So now would be a good time to review your linear algebra. So certainly next week we will get into that. All right, so anything else to discuss today? Let me give an exercise. Okay. So since I made some noises about so we'll finish. Let me just say we'll finish. Okay. Let me just go up over here and see this. So this remark. What we said is that this type of reasoning, taking a finite open cover, some disjoint sets from that, and taking the intersection of those sets. This kind of reasoning can help you do the following exercise. Optional exercise. Take a metric space if you want, because those properties. So then show the following. Do the following. Do the following. Suppose given disjoint compact subsets A and L, this should give a width that is very similar to what we did earlier, right? So here is the picture. Here is K, and here is L, and they're disjoint. So that is K and that is L. So I'm supposed to be able to do this. And the hint is sort of do something what we did, like do something like what we did before. Same type of idea. And maybe one more hint is that you will sort of do it in 2 steps. So here. So in the jargon of topology, this says that any compact Hausdorff space is normal. By the way, okay. I could have replaced this word compact for K and L by another word.
Closed.
Yeah, why?
Because closed subsets in of a compact set is
Right, exactly. Because you see, X is given to be compact, no? So any closed set will be compact.
and in a Hausdorff space, compact subset is also closed.
So in this, so for this X, compact and closed subset is synonymous. If you care, you do this. If you don't do this now, anyway, you will do this in your topology class. Completely standard thing. But the reason to say it is that the type of reasoning that we did over there is a very canonical kind of reasoning. That type of thing comes again and again. And when we prove number 2, we will again see something similar when we prove the tube lemma. So this argument you should understand. Yeah, this argument over here is something worth understanding. How it goes. And so maybe over here, this is the I should let me just say. Just do this. Choose yet another color. So the part that I want here is this one. So this is the U. Okay, so are there any further questions or anything people would like to say? Very well. So let's stop for today. And remember, if you have any questions or anything, or if you know somebody else who may be struggling, do ask them to get in touch with me tomorrow. We'll have office hours at the usual time, same as class time, which is 11:50 to after 1 o'clock. So, all right, bye everyone, and see you on Friday.
Thank you, sir.
Thank you.